Yeah. Welcome everyone. Thank you very much for joining in. So today we have Dr. Mahima Gupta presenting her PhD, part of her PhD work, Smart Switching Power Electronics for High Density Power Conversion. Please put your questions in the chat as detailed as possible, and Dr. Mahima will take it at the end. Or do you want at the end or in between also? Is it fine? Or
in between is also fine.
if it is short, okay. If it's a longer one, you can just pass it on
Right,
to the
I
moderator.
can. Okay. Yes.
So I welcome Dr. Mahima, and please go ahead, Mahima, please go ahead.
Okay, thank you. So I am Mahima Gupta, and I recently completed my PhD at University of Wisconsin-Madison, and I'm currently working at Ford as a research engineer in the Research and Advanced Engineering Group. So I'm located in Michigan currently, and today I'm going to talk about smart switching power electronics for high-density power conversion. Okay. And I would like to point out that this is part of the research work that I did at University of Wisconsin-Madison, which was advised by Professor Giri. So looking at the typical power converter, the power converters can be, this is a block diagram of a simplified power converter. And we can see the block, typical power converter interfaces the source to the load. If we open up a power converter, we see that it is composed of solid state switches and energy storage elements. These switches operate at a certain switching frequency, which is typically beyond 5 kilohertz. On the other hand, these energy storage elements store up to hundreds or thousands of units of energy, wherein one unit is defined as the energy transfer between the source and the load. So if we look at a state-of-the-art typical power converter, this is one such example for a three-phase motor drive application, wherein we see that the switching devices and the energy storage elements. So we see that since a couple of decades, we have been working towards the next generation switching devices, which we call as the wide bandgap devices. So as opposed to silicon, we can use silicon carbide or gallium nitride, which have their intrinsic properties, which are more suitable for power electronic applications. So they can be designed with a smaller die size, which can enable lower RDS on, that is reduction in the conduction losses. In addition, they can work at a higher junction temperature, and together these two properties can help in reducing the overall density, increasing the overall density of the power conversion, and help in compressing the thermal design along with the solid state switches. The second aspect is the energy storage elements, that is the capacitors. So this work is placed right here, wherein we focus on how we can reduce the size of these energy storage elements for future power electronics. So if we look at these power converters across applications, say for example, wind power, electric vehicles, aerospace, solar power, and so on, we can see that the common backbone is that the energy storage elements, which is capacitors in all these cases, occupy as much as 70% of the total power converter volume. So my objective during my thesis was to move towards lean or high density power converters by eliminating the need of these bulky electrolytic capacitors. So here is a topology of an example DC to DC power converter. So this is a simplified power converter that I'm going to discuss throughout most of this presentation. Definitely, we can look at other power converter topologies as well, but I'm using a simple example so as to discuss some of the main ideas of the work here. So this is a cascaded power converter wherein the source and the load are located at the left and the right hand side. We have the associated switches, is the source side switch and the load side switch. The filtering elements integrate the source and the load to the DC bus capacitor via the switches. And finally, we have the energy storage elements. So if we look at each and every one of these components one by one, we see that the switches are typically rated for the power throughput, or in other words, the voltage and the current ratings of the source and the load. As we discussed in just a couple of slides before, as we move towards wide bandgap devices, we can target compact thermal design. The second component, that is the load and the source filters, they are typically specified in order to meet the specifications of the source and the load, which may be in the form of THTs, EMI performance, and so on. As we increase the switching frequency, the size of these source and the load filters can be reduced. The final element, which is the energy storage elements, and we see that typically these are presumed to be big for robust circuit operation. So the question that we would like to ask is, can we do something better? So here is a glance at the typical operation of the power converter, wherein since this capacitor is assumed to store abundant amount of energy, we can assume that the capacitor voltage is essentially a straight line. If we look at the switching functions at the source side and the load side, we see that they may or may not be synchronized. In this case, it is shown that these are synchronized to the center of the switching cycle. The source and the load pole voltages are shown at the bottom. Then we can do duty ratio calculation using the principles of averaging, which is shown right here. So I would like to typically draw an analogy between this typical operation and this example shown at the bottom right here, wherein we can compare this bulky energy storage element to a big bucket of water. The source and the load transfer energy, which is typically insignificant as compared to the energy which is stored in the energy storage element right here. So the first half of our work, the first part of our work was to look at these state-of-the-art approaches and to see, to benchmark them to see that their performance limitations. So one such example of closed loop regulation is shown right here, wherein we discuss an inner current loop and an outer voltage loop. Definitely, depending on applications or design considerations, there can be other hierarchical approaches as well. But we considered this particular example for our analysis. So we started with developing a dynamic model for the regulator by using the state space equations for the state variables. In this case, it is the input current, the output current, and the DC link voltage, which is characterized by these three equations. The switching action of the switches SI and SO are characterized by the switching functions, and using the principles of averaging, the switching action can be averaged, which is shown here using the D1 and D2 duty ratios. These duty ratios, the control regulator characteristics can be included in the duty ratio expression, which is as shown here and can be substituted into the state space equations. After that, we developed the small signal linearized model, wherein we superimposed a small variation in the load in this system model that we are trying to develop. After which we can do a sensitivity analysis. So while we have this equation which is in the form of all the state variables, the particular equation that is of interest to us is the capacitor voltage. So we extract this particular equation and try to find out the transfer function between the capacitor voltage and the load. So this transfer function characterizes how the capacitor voltage reacts to any changes in the load condition. So when we do the analysis and do the math, we see that the solution is pretty heavy and it is not very intuitive. So we try to use some assumptions and some approximations so as to understand get some analytical insights and to develop some design guidelines. So I'm going to talk a little bit about it, but more details can be found in the publications that I'm going to show later. So one of the aspects that we have to be careful about is the system stability. Of course, the system has to be stable, and if we look closely, it is this particular term which needs to be positive for a stable operation of the overall system. And if we, assuming that this denominator has to be always greater than 0, we find out that this Kp has to be less than a particular value. This Kp is the proportional gain of the outer voltage loop. Just to be sure that we know where it is, I will probably just go back and show that this is Kp here. Yes. Yeah. So one interesting thing to note is that we see the value of the capacitance in this Kp. So Kp has an upper bound, in other words, that lower capacitance systems have to have a lower amount of Kp. So one question we ask is this equation valid? So we developed this simulation in a Plex environment just to verify that the model is accurate. So on the left here, right-hand side, the left-hand side, we see that we have a steady state operation. And when we are operating at the boundary of Kp, any disturbance in the system leads to a divergent system that is an unstable operation. On the other hand, if we maintain a safety margin of say about 10%, which is showcased in this particular situation, we see that the system converges to a steady state value. So as a design rule, in order to design regulators, we can develop a safety margin. In this case, it can be 10%, 20%, depending on the application. The other aspect is optimizing the transient peak during transient conditions. So we can show that this system using approximations can be reduced, and it comes out that it is dominated by a single pole transfer function. So now that we have a simplified expression, we can extract the voltage overshoot in terms of the system variables. So the expression is shown right here, wherein we see that in addition to the variables which depend on the power throughput, we again see the impact of Kp in reducing the peak transients. So if we bring these two equations together, we find that on the one hand, in order to have a stable system for small capacitor values, our Kp has to be smaller. But the trade-off is that the transient peaks will be higher and higher. So we can see that there is a theoretical limit to how much we can reduce the size of the capacitor for high performance applications.
Mahima, regarding Kp, we have one quick question from Venkatraman.
Yes.
Venkatraman, please go ahead with the question.
Yeah. Hi, Mahima. This is Venkat.
Hello.
You had mentioned about the stability condition on Kp, right?
Right.
Just the slide earlier. So when you had indicated that there are two control loops, one on the input side and one on the output side. So
yes.
Those control loops have already been stabilized and they have been designed for stable operation, right?
So
because otherwise, yeah.
So this is the architecture that we have. So we have hierarchical control loop, but it is only for the input duty ratio.
Correct.
For the output duty ratio, we base it on a command. Yes. Okay.
Correct. So in this architecture, the fundamental assumption is that the input functions independently of the output duty ratio. I mean, the output stage entirely is going to be reflected as a single resistive load, equivalently speaking. Okay. For the DC bus cap.
Okay.
And any changes in the load is going to be adjusted by the duty ratio D1.
Right.
Such that the capacitor voltage is regulated. So that's the idea, right? For designing the input control loop.
Yes.
Of course, it is hierarchical. Okay. So the question is, so the input control loop design is already going to be stabilized. I mean, for a given value of cap, you design Kp and Ki such that the input loop works stably. Correct?
Yes. Right.
So what is this condition that you had just now elaborated? I mean,
so right. So as you mentioned that our system has to be stable and this loop has to be designed such that our system is stable. So what all we are trying to do is to develop a simple analytical equation so as to ensure that the system is stable. So we
yeah,
are just, right.
Yeah.
I
Okay.
think what he's asking is, when the individual control loops are already stable, what is the new stability condition that you are introducing? What is the need for that? I think that's the question, Venkat. Is that the question?
What is the need? I mean, even before that, is it? I mean, what is the rationale behind this condition over and above what conditions are already existing for the individual loops?
Right. So in this particular example, we are just trying to characterize this classical approach, and we are just trying to develop a simplified equation between the design variables, that is the proportional gains here, to the capacitance value. So we are just trying to map how if we reduce the value of the capacitor, there is a risk of this system going unstable, and how we can make sure that in lower capacitance systems, the system has to be stable.
So the capacitance value is the variable in this case,
Right.
the capacitance value.
Right. Yes.
Okay. Yeah, you go ahead. Yeah.
Okay.
Yeah, thank you very much. Yeah.
Yes. So yeah.
Please go ahead. Please go ahead.
Okay.
Yeah.
So I was right.
Yes.
So this is the time domain simulations, and just to point out that again, now we have this capacitor value, which is 1000 microfarad, and we designed a stable system for this capacitance value, and then we varied the value to 10 microfarad, and then we again redesigned the system such that we have a stable operation. So when we see that when we have a 1000 microfarad capacitor, the energy storage is in the range of 400 units of which is 400 times the energy transfer rate. And for a 50% load rejection scenario, in this particular case, the overshoot is just about 1%. When we do the same exercise for a system wherein the capacitor value is smaller, we see that the performance is poor. So which requires derating of the capacitors and the switches which are connected to the DC bus. So this was a design example which was done for a 20 kilowatt power converter, which was stepping up 200 volts DC to 325 volts AC. And to summarize, we see that as we reduce the energy storage requirement at the DC bus, it degrades the system performance. So once we benchmarked the performance of the state-of-the-art approaches, we try to start afresh by coming up with the idea of tiny energy storage at the DC bus. So we take a more of a bottoms-up approach, wherein we start with the assumption that the capacitor, the energy stored in the capacitor is very small. And by small, we mean that it can be as low as 2 or less than 2 units to say 10 units of energy. So the analogy that we can see on the right here is that we have replaced the big bucket with a small reservoir. The upfront advantage that we can see is that we can reduce the size of the capacitor, but the trade-off is that we have to be careful when we do the energy transfer between the source and the load for high performance systems. So we have divided this task into 3 main aspects, which is shown right here. And I'm going to go through each one of them one by one. So we are looking at a DC to DC power converter example, wherein we have 2 switches. So this means that we have 4 switching states, which are as shown right here. One of the states is when both the switches are connected to the DC bus, and only the net difference in energy is flowing into the capacitor. The other extreme is when neither of the switches are connected to the DC bus and we are freewheeling. The intermediate switches are shown as these 2. So considering one example, which in this case is a step-up operation, we decide that, okay, we have, since our capacitance value is very small, we have to optimize the ripple at the DC bus. So we start with the switching operation wherein both the source and the load is connected to the DC bus. So only the minimal, only the difference in the energy is flowing into the capacitor, and the capacitor voltage charges to a certain value. Since this is a boost operation, the capacitor has excess energy, and during the other half of the interval, we discharge the capacitor of all its energy. Now, since we are looking at fixed switching frequency operation, the source and the load have a freewheeling path, and there is no energy transfer between the source and the load. So we can draw a contrast between this approach and the conventional approaches, wherein in the conventional case, wherein the source and the load switching operation may or may not be synchronized. In this case, we sequence the switching operation between the source and the load. The pole voltages are shown at the bottom. So second aspect is the duty ratio calculations. I'm directly looking at the expression, but I would be happy to discuss the derivation later. But we use the voltage-second balance in order to derive at this equation, which at the first glance looks quite complex. But if we look closely, and if we look at this particular ratio, which is small e divided by capital E, this essentially is the energy transfer to the capacitor divided by the energy stored in the capacitor. For conventional cases, this ratio is much smaller than 1. So if this ratio is smaller than 1, we can use Taylor series expansion so as to simplify this expression. And ignoring the higher order terms, we find that we have converged to the average duty ratio. So the question is, can we use this particular expression or a simplified version of this expression? So it depends on the design problem. So assuming that our small e, that is the energy transfer to the capacitor, is say 0.2 joules, and we are using a capacitance value of 5 microfarad. So this translates into twice 2 units of energy storage at the DC bus. So this factor is going to be half and the error is going to be high. On the other hand, if we use the second design, wherein our ratio is about 10 times, the duty ratio in this case, error in this case was less than 5%. So it depends on the design specifications. So the third and the last aspect is what we call as the capacitor charge restoration. And this has been introduced to deal with transient conditions or inaccurate model estimations and so on. So focusing on the left-hand side of the page, we see that we start from a nominal energy storage or nominal capacitor voltage that we call as Vn. And we saw that we charge the capacitor, we discharge the capacitor, and then we come back to a nominal value. When the energy, there is energy match between the source and the load, which is true in steady state situations, we will always come back to the nominal value. However, in the real world cases, there may be situations wherein when we finally end the active variables, there may be a positive residue or there may be a negative residue. So the question is how to deal with such situations in a converter wherein the capacitance is really small. So looking at the first situation, we have excess energy in the capacitor after the active intervals have entered. So what we can do is we can introduce an extra load interval so as to remove the excess energy from the capacitor. On the other hand, we can map the similar analysis and say that if we have less energy in the capacitor, we could potentially introduce a source interval and charge the capacitor. While the left-hand side operation can be called as the load interval tuning, the right-hand side operation can be called as the source interval tuning. But this has some interesting consequence on the stability of the overall system, which I'm going to discuss in this slide. So we use the theory of variable structure systems so as to characterize the stability aspect of this example. So the delta is defined as the residue. We know that if delta and the delta dot is less than 0, the overall system is when disturbed is going to converge to its equilibrium value. On the other hand, if delta dot is greater than 0, we are going to have an unstable operation. So we can introduce these aspects into our capacitor equation so as to find out what is happening. And we see that when we do load interval tuning, our delta delta dot is less than 0. On the other hand, when we do source interval tuning, our delta delta dot is greater than 0. So if we do source interval tuning, we have to be careful because this leads to an unstable operation. So this has been verified again using circuit simulation, wherein we see that for a simple DC to DC power converter example, when we do load interval tuning, we have a stable operation. On the other hand, when we attempt to do source interval tuning, the system starts to diverge. So looking at the overall performance, while the results which are as shown right here are copied from the previous slide, wherein we compared the 400 units energy storage situation to 4 per units energy situation. And now when we look at the proposed approach, when we introduce a 50% load rejection scenario, our overshoot is less than 2%. So now we can say that with the use of this proposed modulation and control approach, we can achieve higher performance even with low values of capacitors. So the consequence of this is as shown here visually, wherein this module represents the half bridge circuit, and we see that we're using a small capacitor as opposed to a bulky capacitor. I'm going to talk about this in detail in just a few slides. So up till, I'm going to pause here for a moment just to see if there are any questions.
Yeah, I had one question. When you talk about negative residue, how is that caused, and how are you trying to mitigate that? Is there a reversal? Here.
Yes.
When you say negative residue, how is it actually caused?
Yes.
Negative charge? Polarity?
Yes. Right. So while in the ideal situation, the source and the load energy requirements are completely matched. But say, for example, when there are any transient conditions, suddenly there is a load rejection situation or load addition situation, we may land up with a positive or a negative residue, which means that the source is trying to supply the energy or the power, but the load does not want to take it. Or it wants to take more and more. So that is why we have called it a positive residue and negative residue.
Okay. So basically load potential is higher.
Right.
In this case. Okay.
Yes. Yes.
Yeah. I think we can go ahead.
Okay.
There are no more questions related to this. I think at Q&A people will post more.
Okay. Yes. So looking at AC conversion systems, we can extend this analysis that we discussed for a DC to DC power converter to AC conversion cases. So on the left, we have a DC to AC power converter. On the right, we have an AC to AC power converter. So while in the conventional cases, we have a capacitor which stores quite a bit of energy, the capacitor voltage looks like a straight line. However, when we have a small value of capacitor, we can no longer call our voltage to be constant. So we can apply the same principles and say that we have to do a coupled modulation between the source and the load so as to not overwhelm the capacitor, or so as to manage the energy which is transferred to the capacitor. Hence, we will end up with a predefined or very distinct charge-discharge charge-discharge pattern at the capacitor. So we can use the principles of, say, space vector modulation, or what we introduced as two-phase equivalent system approach, so as to extend the analysis. So I'm not going into the details, but I would be happy to discuss or refer you to some publications. So directly going into a photovoltaic design example. So we implemented this approach for a transformer-less DC to AC power converter, which was a 3.3 kilowatt power converter, stepping up 200 volts DC to 208 volts AC. And while in the conventional cases, we may use, say, 1000 microfarad capacitor. For the proposed case, we designed it with only a 10 microfarad capacitor. So this power transfer operation represents about a third of a joule of energy transfer. We can see that the energy stored, in the 10 microfarad capacitor is just a little less than 2 per units. So here is the simulation results, wherein focusing on the steady state scenario, we have a constant load and we can see the high quality of the output currents. The voltage ripple is less than 6% at the capacitor voltage. And then we introduce a load rejection scenario, and we see that the currents converge to a lower steady state operation value. And the ripple at the DC bus is smaller, about less than 3%. We can see that the overshoot in this situation of 100% load rejection scenario was less than 4%. On the right, we see the high frequency waveforms, wherein the top 4 waveforms represent the switching functions of the source and the load side. And we can see that these switching functions are sequenced and synchronized in a particular fashion. And another highlight is the capacitor voltage right here. And we can see a distinct charge-discharge pattern at the energy storage element. Also, these are the pole voltages at the source and the load side.
And what was the switching frequency in this case?
In this case, we limited it to 10 kilohertz.
Okay, but is it relevant to switching frequency, or does it depend on switching frequency? But I think power converters, you operate less than 50 kilohertz, right? So can we go like 10 to 50?
Yes, we can do that. Yes. So the prototype that we developed, we operated up to 50 kilohertz. We can definitely use that approach, but we used 10 kilohertz operation.
Okay.
And one of the reasons that we wanted to do that was that we wanted to show that even so the conventional thinking is that when we in fact, which is true, that when we increase the switching frequency, we can reduce the size of the energy storage elements. And also what we wanted to emphasize, that even with a small switching frequency operation, we can reduce the value of the capacitor. But definitely the switching frequency is not a limit in this situation.
Understood.
So here is the laboratory prototype which we developed, and it was a modular design wherein each of these modules, this particular module represents a half bridge along with its auxiliary circuitry. And we were doing a DC to AC power conversion scenario. So that is why we have 4 boards which are sitting on what we called as a motherboard. And we used some silicon carbide MOSFETs, and this was rated for up to 700 volts DC bus and we tested up to about 2 kilowatts of power conversion. And this is the laboratory prototype from the lab, and the setup is sitting right here in the cabinet. And here are the waveforms from the laboratory prototype at about 2 kilowatt operation, wherein we can see the high quality of the 3-phase output and the voltage waveforms. The high frequency switching action is shown right here, and the 1-to-1 mapping can be observed. So the next question that we try to ask is, can we go to the next step, that is a lean square operation? And some of you might have guessed that could we do 0 units of energy storage at the DC bus? The analogy which can be drawn is that we have gotten rid of the reservoir or the bucket of water that we had in between the source and the load. So the advantage is that for this particular situation, we need less than say fractions of microfarads of capacitor, and the capacitor voltage looks right here, wherein as opposed to conventional cases wherein there's a straight line, it looks we charge and discharge the capacitor at the end of every high frequency switching cycle. One of the interesting points to note is that this particular operation sets an upper limit on the value of the DC link. And this is because the capacitor should be small enough such that we can discharge it at the end of every high frequency switching cycle. The upfront trade-off is that the peak value in this case is much higher. So the devices have to be rated for a much higher voltage. So I'm not going into the details, but directly looking at a design implementation that we did for a small 100-watt fan, which is shown right here. And we were using a 39 nanofarad capacitor, and the capacitor is sitting right here, wherein we can see the small size of it as compared to, say, a typical TO220 package that we were using for our converter operation. The contribution of this work is that we wanted to reduce the size of the capacitor such that it's as small as possible. And this is what we attempted to do, wherein we no longer need abundance of energy storage for a robust operation. So in summary, to summarize this smart switching idea, if we plot the energy storage in terms of units in the y-axis and the control bandwidth in the x-axis, in most state-of-the-art approaches, our control bandwidth is typically much slower than the switching frequency. So the fundamental idea is that when we move to a faster control bandwidth, wherein our control bandwidth is much faster than the switching frequency, we can reduce the energy storage at the DC bus. And in the example that we showed here, that as opposed to the classical approaches, we can use small value of capacitor. And in this case, the performance matrix was overshoot, and we can limit that within a certain value. In conclusion, these approaches, the two approaches that I discussed here, enable 2 orders of magnitude reduction in the energy storage for capacitor elements. This can also be extended to current source power converters. And instead of using several microfarads or millifarads of capacitor, we can use a few microfarads. And in many applications wherein we are in the habit of using electrolytic capacitors or many film capacitors, we can use small number of film capacitors which have a higher lifetime and lower losses. So this work lays the foundation of new directions for high density power conversion, which is not limited to photovoltaic application that we discussed, but it can be extended to several other applications. And one such work that we are doing is extending this to an electric vehicle application, which is a part of the UW Madison work which is going on. Here's a list of the references that I used and some of the publications that we did related to this work. And that's my presentation.
Very good. Very interesting work, Dr. Mahima. Very well presented. Thank you very much for the detailed presentation. We'll take quick questions. We'll take quick questions from the audience. I think we have Venkat. I think Venkat. Please unmute yourself and go ahead. Yes.
Hi, Mahima. So, one question on the size reduction that you had shown for the PV system, or in general, you had shown that there's a large electrolytic cap and then it gets reduced to a small sized, film cap or something like that, right? So,
go to that slide.
Yeah. Can you go to that slide?
Sure. Like this one? Is that a good?
Yeah. So I think, there are some caveats that you need to actually add, right, for this kind of size reduction. For example, let's say you have a PV front end and then you have a single phase inverter feeding a grid or feeding some loads. So then you will have a large, low frequency ripple that is flowing.
Yes.
And your proposed method will not work if you have low frequency ripple on the DC link current, right?
Yes. So right now I understand, but we have some ideas on how to extend this to say single phase applications wherein the energy stored, energy transfer between the source and the load is not matched at all instance of the fundamental cycle. So as you rightly pointed out, in fact, there's an interesting point to make is that we are currently working with 3-phase systems, And this comes with the assumption that if you look at every instant of this three-phase energy system, the energy requirement by this three-phase system is constant. But in the case of a single-phase system, as you pointed out, the energy requirement is not constant. So we did brainstorm for this the example, like you mentioned, for say single-phase systems. So we did have some ideas, but we did not really implement that. But yes, this is one of the, I agree, that limitations. It has not been extended to such systems wherein we have low frequency components.
Okay. So one is regarding that. The other thing is, for example, when you have DC input and three-phase output, then sort of, the power flow is may get balanced out, but still you will have some ripple that is flowing through the cap.
Right.
And what is your opinion on the current ripple capacity of the DC bus cap that is required? Because many a times it is not the voltage ripple that is the determining factor for sizing the DC bus cap. Exactly. It is also the ripple carrying capability. So when you put a small, ceramic cap or a film cap, whatever you have mentioned,
yes,
it may not suffice the actual application, right?
Yes, right. So I completely agree. And the reason that we move towards this very low capacitor is like I pointed out here, that we are saying that we will just use say 2 units of energy storage. So definitely we were using more of like a bottoms up approach, wherein we go as aggressive as possible and then we go from there, as opposed to using as bulky capacitor and then shrinking it down and down. So definitely, when we are looking at a particular application, which is very specific. So right now we are looking at a traction application, which is a collaboration project between Ford and UW-Madison. We are indeed looking at a particular specific application wherein we have one DC to DC converter, one motor, one generator system, and what other system application specific system constraints come into play so as to design this capacitor value. So definitely this was more like a bottoms up approach, going as minimum as possible and trying to prove that, okay, for a particular application, for a particular design example, this works. Okay. Definitely when we are looking at more other applications, there may be situations of fault right through conditions or source wherein the source goes away, what happens? So such application specific situations need to be taken care of. And then the capacitor size may have to be increased because of the constraints which are put by the application.
Yeah, one is the application, the other one is the PWM itself. For example, if you have continuous currents on one side of the power converter and you have switching currents on the other side of the power converter.
Yes.
So it's the capacitor which is actually taking the ripple, and
right. Yes.
And I mean the value that you the value reduction that you are saying is theoretically true. If you, for example, if you don't consider the current stress that the switching ripple is going to put on the cap, then it is true. But it's actually a multi-constraint problem, right? It is not just.
In fact, I agree, because what happened, the interesting thing that happened was then when we were trying to find this capacitor value, like I showed in the prototype. So when we were looking at this capacitor value, we wanted to use 2 microfarads of capacitor and say that we have a stable operation. And we were able to even find a capacitor which can handle that much amount of ripple current. But the problem was that it was not available. There was a part which existed, but because there is no need, or probably the requirements of such small capacitors with higher ripple current is so low that we couldn't find it in the market. Right. So because as a community, we have always been sizing, definitely, which goes with it, that if you want to carry a certain amount of ripple current in the capacitor, we end up with a bigger value of capacitor. So there are some real world challenges to it as well, which in fact I also faced when I was trying to find as small of a capacitor as possible.
Right.
And then now, in addition, there are there is some work going on wherein we look at active capacitor cooling schemes. So moving towards high density power conversion, in many applications, we cool the switching devices, but we not always cool the capacitor. Because we're using a big capacitor which has a bigger footprint, and the natural convection or natural cooling is enough for it. Now, as we move to a smaller capacitor value, and we are really looking at high density power conversion, we can also introduce such cooling schemes such that we do not need a bulky capacitor, but we can do with a small capacitor, which ensures stable operation, high performance operation, and is still smaller and can handle the ripple current.
Okay.
So I completely agree. There are some real world problems that we did face, but our main objective was go as aggressive as possible and see what best we can do theoretically. Definitely, as we move to applications, there are some real world challenges.
Okay. Thank you.
Thank you for pointing that out. I should have probably made it.
Yes. Yeah, you can just introduce yourself and what your current line of research is, so that Dr. Mahima knows what is happening here.
Yeah, I am Venkat Ramanan. I finished my PhD in IISc Bangalore last year. Now I'm a research fellow working in the area of ultracapacitor based energy storage systems in IISc. Yeah.
Okay. Very interesting.
Thank you.
Thank you very much. Thank you for your question, Dr. Venkat Ramanan. Rishabh, can you please go ahead, Rishabh?
Hi, hello.
Go ahead, Rishabh. We can hear you.
Okay, so since we are reducing the size of capacitors, and I'm talking about photovoltaic application, in photovoltaic application, there is a keen aspect that you should follow maximum power tracking. So since DC link voltage ripple, I don't know how the impact is when we are shifting from a higher size capacitor to a lower size capacitor. I assume the link voltage ripple will increase. So how is it impacting the power point tracking?
Yes, so I would confess that we did not really implement maximum power point tracking algorithm in this particular case. But one thing that I would like to highlight is that, again, our energy storage is less than 2 per units. So definitely our ripple is in the range of 5.5%. So, I cannot really comment on the MPPT part of it. But again, it was as the application implements its requirements, specifications, we have to work closely with that application to see how we can fit these two together.
Okay.
Okay. Rishabh, you can introduce yourself to Dr. Mahima so that she knows what is your background, what are you trying to do here.
Yeah, I work with a company called Sangro, and we are into renewable inverters, basically for solar and wind systems.
Okay. Okay. Thank you.
Thank you very much.
Adrish, please unmute yourself and go ahead. I think he has a question in slide 29, I believe. Adrish,
yes.
Here?
Hello, ma'am.
Yes. Please go
in
ahead.
slide 29, I have a question that for AC side, as we have explained that for reducing the capacitor, I have to control over the PWM. But in AC side, if I consider a inductive load, then my sine PWM or SV PWM, it will be designed based on the load side performance. So if that is based on load side performance, then how can it will implement or interlink with the capacitor reductions PWM? I hope I'm not getting the point that how these things can be interlinked, because PWM or the SPWM I will design on the
Adrish, your audio is breaking up a bit. So let me summarize. Are you asking how this approach is useful for, can you just repeat the last portion? We missed the last portion. Your audio broke up.
Sine PWM or HPWM, whatever we do in the AC side, that will be designed according to the load side performance. So if I want to design a PWM which will reduce the capacitor size, then how can it interlink? Am I able to clear my point?
Okay, I think Mahima is asking what was the constraint chosen to size the capacitor? Which switching scheme? Which switching scheme? Is that right, Adrish?
No. That is not my question.
One
That
second.
sine PWM or HV PWM.
One second, Adrish, what you do, your audio is breaking up a lot. Just type it out in the chat. We'll take the next question and we'll come back to you. Okay, just type it out in the chat. Your audio is breaking up a lot. Okay, we'll come back to you. So, meanwhile, Jeet, can you please go ahead? Hopefully, I'm pronouncing it right. Jeet? Yeah. Please go ahead. We can hear you.
The name is correct. I think the Adrish, I have the similar question with respect to what Adrish is asking. My
Okay, go
question
ahead.
is, if I use a motor as a load, if I use motor as a load and I have a defined switching pattern as like SVPWM or SPWM, then will this topology work in helping me reduce capacitor size?
Yes, so I would say yes. In fact, like you mentioned, we can use space vector diagram, and again, this three-phase system can be reduced to the vectors, which is imposed by the load, that is the current vector, the voltage vector, and then we can use the schemes that you want in the case of for your load requirements and implement that. So although I did not go into the details, I have discussed that in some of my publications, but some of the main ideas remain the same. So we can have an optimization variable, which can be reducing the ripple at the DC bus or improving the performance of the load. But one thing that we have to be careful is that when we are transferring the energy from the source and the load, the energy mismatch has to be managed. So definitely we can, in fact, we did that for a motor drive application, and we can do that, yes.
So if I am correct with your explanation, that using I can use my PWM schemes, and only the point is that if I use a closed loop application wherein my load, my source is also looking after the load, and accordingly my duty is changing. Is it what you are trying to say, madam?
Can you please repeat the last sentence? My apologies.
Yeah,
I just...
Jeet, there's some noise. Yeah, just repeat the last. Yeah.
Yeah, I'll repeat my last statement. My last statement was that in the closed loop scheme, with the changes in my load, my source will grab those change and accordingly define its own PWM pattern to compromise the roundabout effect.
Okay, he's talking about transient. What happens when you have a transient?
Yes, for transient. So let me go to this DC to DC example, and I think we can extend the principles right here.
Is that what you're asking, Jeet? Whenever
Yes. That was accurate.
okay.
Yes.
Okay.
So at least up till now, how we have implemented is that we are operating the source and the load at the same switching frequency. For the application that you may be referring to, the source and the load may be operating at a different switching frequency. But at least up till now, how it's developed, they are operating at the same switching frequency, and the switching functions are synchronized, which is as shown here. But and then we can use duty ratio calculations, as I discussed, and then we can use this capacitor charge restoration algorithm so as to handle those transient conditions. But all of these vectors, all of these, while this is the DC to DC situation, we can extend this to AC cases, and instead of, say, we are using space vector modulation, we can have a voltage and the current vector. So we can select two vectors and then implement the same idea of sequence switching and then go from there.
Does it answer your question?
Yes, partly. Ma'am, if I have more doubt regarding this, is it fine if I mail you? Because I'm
yes, sure.
Yes.
Sure.
Please, please go ahead. Yeah.
Last thing, as a suggestion, if like as an advice, like or a suggestion, that if we will be using a super fast capacitor or as we say ultra fast capacitors, will performance as in transient state increase?
So we are using Like supercapacitors, is that what you say?
Yes, yeah. Instead of you using electrolytic, right? What if it is replaced by supercapacitor? Is the same behavior observed in that? I think it should
I
be
would say
same.
so. Yes, I would say so. The only reason why I highlighted electrolytic to film is that typical applications need, say, millifarads of capacitor, and we can't really use film capacitors. But I don't think it's a strong. The operation of this technique is a strong function of which capacitor technology we use. It is independent of that. But this is one highlighting point that I made. So you're right.
Okay.
That
Jeet, yeah, please go ahead and email. Dr. Mahima will
Yes.
be more than happy
Yes.
to answer.
You can email me
Yeah, we have
using either of the email IDs.
Yes. Super.
Thank
Yeah, thank you, Jeet. Rishabh Anand has one more question. Can you describe the switching sequence in the energy scenario?
Oh, your voice went away. Could you please repeat? Hello? Hello?
Is it fine? Can you hear me now?
Yes, I can hear you now. Yes.
So Rishabh Anand is asking, can you describe the switching sequence in the zero energy storage scenario?
Yes. I wish I had more slides on that.
Yeah, Rishabh, you can go ahead, unmute yourself and go ahead. Yeah, yeah. Is this the one?
Yes, I just wanted to understand the breakup of how this delta zero part is there.
Yes. Is there a way to annotate here or? I
think I have disabled that. Yes.
Oh, no problem. Okay, so let me open up one of the papers so that I can use the.
Yeah, sure. Others, in the meanwhile, please post your question here. We can take quickly one last question.
I am just one moment.
Yeah. Please take your time. Let me. Yeah, maybe you can share your entire screen. I think now you're sharing a window.
Yes.
Yeah.
Now.
Yeah, I think you can stop sharing and then share your entire window.
Oh, new share. Okay.
Yeah.
Screen.
Yeah, just screen.
My apologies. I'm new to.
No problem. Yeah.
Now can you see?
Yes, we can.
So I can summarize a little bit. So the zero unit energy storage is highlighted in this blue waveform that is shown here in the paper. And now we see that we have a charge, capacitor charge, and then second discharge, and then the third discharge. So this example, just to point out, it represents a DC to three-phase AC system. So now this charge is represented by the situation when the source is connected to the capacitor, and then it transfers energy to the capacitor, which is a predetermined value. And then during the remaining interval, the capacitor has two switching, the three-phase load has two switching states. So it can be, say, 100 and 110, for example. So that is implemented, and that discharges the capacitor, and then finally discharges the capacitor completely during the very last interval. And then we have the zero state scenario. So this is the capacitor voltage. This is a typical capacitor voltage that we can see for zero units energy transfer, and the pole voltages look like that. So this is an example for a source pole voltage, wherein we see the charge and then discharge, and then it is zero during the remaining interval. So as opposed to, say, a rectangular waveform, in the face of conventional pulse width modulation, we see that we have some sort of a trapezoidal waveform for this power transfer operation.
Does that answer the question, Rishabh? I hope.
Yes. I'll look at the paper also.
Yes. Okay.
Yes. Thank you so much.
Yeah.
Thank you.
We'll let Dr. Mahima go. Excellent presentation, Dr. Mahima. Very good. Thank you for answering all the questions.
Thank you for the invitation.
Yeah. So please email Dr. Mahima. Please go to the paper once in detail. I think, is your thesis online, Dr. Mahima? I think it is restricted to Wisconsin, this thing, right?
But
Or
I think
embargo.
it should be available via the your university, I would say, subscription. Like,
Okay. Understood.
I
Yeah.
feel like it should not be hard to find, is all I can say.
Not on any embargo or anything, right? It is.
I will have to check.
Yeah. Because.
But the rest of the papers are in IEEE, and the first one is in IEEJ,
Yes.
which should be easily accessible.
Good. And what are these patents, Dr. Mahima? Are these related to?
Yes. So this is so we patented the two ideas of zero energy modulation and non-zero energy modulation. So this is highlighted in the two applications, the two papers.
Very good.
Patent, sorry.
Good. Very good work, Dr. Mahima. Thank you for the presentation. And thank you everyone for attending. It's really incredibly hard to get engineers from industry to spare their time. And we thank Dr. Mahima for spending the time to explain her work.
Thank you so much. Thank you for the invitation, and thank you for the good questions. It was a pleasure to be here.
Thank you everyone. We'll end the meeting now. Thank you very much.
Thank you.